Well, hello and welcome to Monday Night Calculus. Your questions, our answers. I'm your host, Curtis Brown. I work at Texas Instruments, and I am so excited that you all have joined us this evening. I just once again want to encourage you and thank you for all the hard work you're doing with your calculus students. And if we have students who have joined this evening, I also want to just welcome you. Please feel free to put questions in the chat box. We'll be monitoring that as we go along. This evening, I'm joined by Steve Kokoska, former Chief Reader. Steve, I'm so excited that you are here this evening. And a little bit later on, we'll also have Dr. Tom Dick from Oregon State University. He was a former calculus committee member, test development committee member, and really excited to have him come on and share some calculus calculator tips and things related to the questions that you all have asked and posted. Steve's been doing a great job this fall collecting your questions on the Facebook page, kind of monitoring that and looking for things that he could talk about. And so that's what we're going to be addressing. But before we get into that, I just want to encourage you on a couple of things. First of all, if you would please, can you put just where you're looking from, the place where you're watching from this evening, and maybe how many sections of calculus you're teaching this evening, or this year, rather. Probably not this evening. I don't think any of you guys are actually teaching right now. Maybe you're having a live stream class, I don't know. But anyway, hopefully we get a good number of you guys responding to that. And then throughout the evening, I'll be inserting some things. And please always feel free to ask questions in the chat. We'll be monitoring that and make sure that I get those over to Steve and Tom as needed. All right, Steve. So I think we can go.
All righty. I'm going to share my screen here if I can. Let's see if this works. How's that look? Okay.
Yep, that looks great.
Fantastic. Well, thank you, Curtis, once again for sponsoring this again this year. It's delightful to work with you. We are doing things a little bit differently this year. We're not going to do any direct content presentations. But as you know, I've been monitoring the AP Calculus teacher Facebook page. And there have been some great questions there, and we're going to try to answer those questions. And some of those questions and answers might lead to some content presentations. So I'm going to continue to monitor that site. But Curtis, would it be okay too? Is there a way for listeners, watchers to send questions directly to you or to us?
I would certainly be happy to field questions and send them over to you. My email address is readily available. It's easy. It's curtis@ti.com. I'd be happy to manage those questions as they come in and make sure that I get them to you and to Tom, and we kind of discuss those. So if anybody wants to send those, I'm happy to have my email address out there. It's pretty simple. curtis@ti.com.
Fantastic. Thanks, Curtis. Let me apologize before I begin here. One thing I did not do this evening is I did not put the names of those people who are associated with these questions. I'm sorry about that. I'll try to make sure that I do that next time. It seems reasonable that there were a lot of questions about limits as everyone, as teachers, students begin the year. They usually begin by looking at limits, which will lead them into derivatives eventually. So there's some great questions here, and I'm going to take a look at a few that were on the Facebook page. And here's the first one. And the first one actually was a two-parter. So this one started out with the limit as x goes to infinity of this product, e to the minus x times the cosine of x. And there was a question about, well, how the heck do I solve this one? Well, I thought about this a little bit, and as x goes off to infinity, I thought about what is each one of these terms doing? As x goes off to infinity, the e to the minus x is going off to 0, and the cosine of x is oscillating back and forth between -1 and +1. Well, that's nice information, but it really doesn't tell me enough yet about what this overall limit is, what the limit of this product is. So I started by rewriting this in a little bit different way. I wrote this as the limit as x goes to infinity of the cosine of x divided by e to the x. Now I feel a little bit better. I think I know a little bit more about this. The numerator here again is going between -1 and +1, but what happens to this denominator as x goes off to infinity? Well, e to the x goes off to infinity, and pretty quickly. So the denominator is increasing without bound. The numerator is bounded between -1 and +1. And so it certainly seems like this limit should be 0. So I'm going to put a little question mark above there. It certainly seems like that should be 0.
Makes sense to me.
So how can I show that? How can I be a little bit more precise? And this is a great question because we've seen a couple of questions recently on the AP Calculus exam that have involved the squeeze theorem. And this is a great candidate for the squeeze theorem. So if I think a little bit about this, I can actually sandwich or squeeze this quotient between -1 over e to the x and +1 over e to the x. And these two I have a handle on. As x goes off to infinity, e to the x is increasing without bound, driving that whole fraction to 0. And similarly here, there's no negative sign out in front. As x goes off to infinity, 1 over e to the x is going to 0. So that means these two pieces, these two ends here are going to 0. And so by the squeeze theorem, the expression in the middle must also be going to 0. So that's a great, I think, question to start out with. And I'm going to pose a question out there. Curtis, maybe somebody can answer this in the chat. I think I saw someone on the Facebook page mention something about using L'Hopital on this. So I'm going to pose the question, why can't you use L'Hopital on this problem? And while you're thinking about that, I'm going to look at this graph.
Okay. Well, Steve, while you're scrolling down to that, I just want to call out the fact that we've got a few students in the room tonight. We've got several teachers. Good. Yeah, we've got several teachers that have multiple sections of both AB and BC. A couple of first-year calculus teachers. So welcome, Brandon. Super excited to see that you're on here. Andres is a student from Florida. Really excited to have you in here. Not that we're not excited for everybody. We are excited for everybody. I'm just scrolling through as quickly as I can to call out some of the students and teachers. And so I'm really, really excited to have you guys joining us this evening. And again, just put questions in as you have them, or if you have questions about what Steve's talking about directly, we're looking for that. And certainly answer his question that he just posed about why we can't use L'Hopital. I've already got one answer. I'm going to hold off on calling it out until I see a couple more.
Okay.
And welcome, Tom.
Hey, Tom.
Excited to have you.
So Tom may be able to do a little bit more with this. Tom, just tell me when you want to take over and do something with technology. But this is just a quick visualization of this squeeze theorem. So this blue curve, if you can see my colors, is this quotient cosine of x over e to the x, and it's sandwiched between those other two functions. Now, look, I've only gone here from 0 to about 5 on this graph, and of course, we're interested in what happens as x goes off to infinity, increases without bound. But this gives you a quick idea of how quickly this expression gets sandwiched close to 0. So let me answer, at least, Tom, if it's okay, let me answer the second part of this question that was on the Facebook page. And then if you'd like to do something with technology on this one, that would be fine. This is actually the second part of the question that was on the Facebook page. The limit is theta goes to 3 of the square root of theta minus 3. And I have to tell you that I would never ask this kind of a question of my students. I would think this is kind of a sneaky question. Because you got to think about this a little bit and note that this function here, this is not defined for theta to the left of 3, because I can't take the square root of a negative number. So this overall limit here right away, just by noticing that overall limit, I have to say, does not exist. Now, this may have been a mistake in the Facebook page. But, you know, this ties together with something that I'm going to, I hope, Curtis, finish up with at the end of the evening. So that limit does not exist, in my opinion. I think this is the one, perhaps, that is a better question. What's the limit as theta goes to 3 from the right? Well, this expression is continuous from 3 on out. And so all we need to do here is to simply substitute in a 3. So this is simply just 0. So that one does not exist up above. but the one-sided limit is equal to 0.
And Steve, I think that also ties to what was going on in the first question. We got several responses now as to why we can't use L'Hopital's rule. First one being the numerator doesn't approach 0, so we've got L'Hopital not applying, which I think is related pretty well to doesn't meet the requirement of an indeterminate form, or that it's not one of the acceptable indeterminate forms. And even Wanda calls out the limit of cosine as x approaches infinity does not exist.
Very good.
And so we've got a myriad of good answers, I think, to that. So awesome stuff.
I would say that it is not in indeterminate form, and therefore we cannot apply L'Hopital's rule. It's not 0 over 0. It's not infinity over infinity. We all know that there are other indeterminate forms, but those are the only two that are required on the AP Calculus exam. Excellent. Tom, can I take a look at number 2? Is that all right with you?
That's fine.
Okay.
By all means.
All right. I think this is a great question also. We frequently see questions like this on the multiple choice portion of the exam. There have been occasional questions like this on the free response portion. I like this one a lot. This one is find the limit as x goes to 3 of this expression, 4x minus 12 divided by that square root. Well, one of the first things we might try is direct substitution. And if we do that, we get 0 over 0. I'm cautious here about writing things like equals 0 over 0 now because the AP program doesn't like us to do that. But in my mind, at least in my class, if I try direct substitution and I get 0 over 0, that's a signal to me that I need to do something. Whether it's L'Hopital, whether it's factoring, whether it's some other trick, I don't like to use that word, but some other method, some other technique. It's a signal that I need to do something. So I thought about this for a little while, and I tried to factor both the numerator and the denominator completely. And the numerator is pretty easy. I've got 4 times x minus 3. And in the denominator, I've got the square root of x minus 3 squared. You have to be a little careful here. What's the square root of that x minus 3 squared? Well, by definition, it's the absolute value of x minus 3. Now, it sounds silly, but I always tell my calculus students, whenever you see a limit problem, a derivative problem, an integral problem with an absolute value in it, before you actually do the calculus, you have to work to get rid of that absolute value in some way. So this begs us to look at one-sided limits. So I can't just reach a conclusion here yet. I'll put an equal sign and a question mark. We need to examine this limit from both sides. So I'm going to take a look at the limit as x goes to 3 from the right, first of all. The numerator is going to remain the same. As x goes to 3 from the right, what's happening with that argument? As I approach 3 from the right, x minus 3 is positive small, but positive. So the absolute value of that positive argument is just that argument, x minus 3. Now I've got some nice cancellation here, and I've got the limit of a constant function, 4. And so that one-sided limit is just 4. Okay, the limit as x goes to 3 from the left-hand side. Now I'm approaching, whoops, I'm sorry about that, Curtis. I'm approaching 3 from the left-hand side. This argument now is very small, but small negative. How do you take the absolute value of that negative argument? You have to take the opposite of it. So there's that negative sign, and okay, in non-calculus lingo, I got rid of the absolute value. Now I can still do some canceling, but this time I'm left with a minus 4. And the limit of that constant, of course, is minus 4. Since these two limits are different, the overall limit does not exist. Great problem. Excellent limit problem involving an absolute value, a little bit of recognition here, knowing to factor that, seeing to factor that, but a very nice problem. And Tom knows this, Curtis knows this. I like to visualize things too. You know, that original expression looks awfully complicated, but you know what? If you were to plug this into your calculator and graph it, it's simply 2 line segments at 4 from 3 on out and minus 4 from 3 to the left. And if you can't see, there are open circles here, and it is not defined. This expression is not defined at x equal to 3.
See, that's a great problem.
I like it.
And yeah, because it definitely does not look like it should come out as two horizontal line segments.
Absolutely.
And we had a couple of people even post that they use this in class today as part of their homework. And so maybe they'll be able to show this little clip of this live session to their students tomorrow as an explanation if they get some questions on that, because I love this question. We also had one person who said they met you just before your book came out and they love your book. So that's pretty awesome. So Marlene,
can we send them something, Curtis?
I mean, that's up to you. So Marlene is reached out about that. So
thank you very much. Appreciate it. Thanks for the kind words. Tom, can I do another one?
Absolutely.
Okay.
I'm enjoying it.
This one.
Tom, you sure you don't want to do a calculator thing here in a minute?
Sure, I can do that.
This is let me try this one, Tom. This is a great question. This is an absolutely great question. There's a lot of cool calculus theory, I think, going on here that deals with limits. Composition of functions, I think, is always a little tricky. I may have taken a little literary license with some of these graphs from the Facebook question, but this is what I got out of it. So over here on the left-hand side, I have a graph of y equal f of x. Over here, I have a graph of y equal g of x. I think the original question posed was this one-sided limit, but I'm going to ask another one here too. Curtis, I'm going to ask you to help me with that second one when I get there, okay?
Okay.
So how do we attack this? This is the limit as x goes to 2 from the left-hand side of g of f of x. Well, I'm going to think kind of naively about this a little bit. And let's see, as x goes to 2 from the left-hand side, my graph is going to get a little messy here, Curtis. I'm sorry about that.
That's okay.
As x goes to 2 from the left-hand side, let's see. So x is going to 2 from the left-hand side. So I'm approaching 2 like this. What is f of x doing? Oh, here it is. F of x is doing what? It looks like it's approaching 1, right? So it seems like this answer should just be, well, g of 1, shouldn't it?
Yeah.
And if I look over here, g of 1 is equal to 0. That kind of looks like that's what the answer should be. But not so fast. How did Ed McMahon used to say that? I've forgotten. Not so fast. That's not quite right. And let's pose that
question
to everybody. Why is that why is that an incorrect reasoning? Do you know why that's wrong? Why that is not the correct?
So we're approaching positive 2 from the left.
Right.
And wait a minute.
So why isn't that just g of 1 equal to 0? I mean, that seems like a reasonable thing to do. Why can't you do that? I'm going to leave that question.
Well, okay.
We'll leave that question open.
Okay, I'll leave it open, but I think I know the answer now. I had to think about it.
Quick question, Steve. Did you mean g of -1? Or excuse me, g of -1?
No.
No, I don't think so.
He means g of +1.
Because as x goes to 2 from the left, right here, f is approaching 1, right there, I believe.
Yep.
Okay.
There we go. Tyler Berman says g of 0 has, well, g of 0 doesn't have 2 possible values, but it has a differing value as you approach it from the left and the right. And that's what we've got from several folks coming in now.
Okay. So
g of 1.
What is
Sorry, g of 1.
What does that mean about the property of g? What property of g don't we have here at x equal 1?
Well, continuity is
Beautiful.
1.
Beautiful. So we can't say this. We can't just plug in a 1 there because we don't have g continuous at 1. So here's how we have to argue here, okay? As x approaches 2 from the left-hand side, what's f of x doing? Well, f of x is approaching 1 from the right-hand side. So I'm going to scribble a little bit over here. That means I have to look at the limit as t goes to 1 from the right of g of t.
Of G of T. Mhm.
Right. So, all right, maybe I should have made this a T here, but I'm getting closer and closer to 1 from the right. What is G doing? Well, it's approaching 3. So this answer here, this limit does exist. This limit is equal to 3. It's not G of 1, and it's not G of 1 because G is not continuous at 1. And that's a great question.
Oh, I like the way that this last person posted it. K Charlwins says it's still the limit, but it's going towards 1 from above or from the positive side.
Yep, very good.
Yep. I like that one.
Excellent. So if I want to find the limit, it seems reasonable to ask, what's the limit as x goes to 2 from the right-hand side of this composition? Well, let's see. As x approaches 2 from the right-hand side, what's f doing this time? Well, it's constant at -1, isn't it?
Mm-hmm.
And so now the question is, can I just plug in -1 here and look over here at the graph of G and get a 2? Is that a reasonable thing to do? Is that okay to do? And the answer is yes. And the reason is because this function G is continuous at -1. So that's a really good question, which emphasizes this idea of how we take the limit of a composition of functions. It was a great question with the graphs on the Facebook page. Good question for your students tomorrow morning when they come in at 8 in the morning, ready to go. Okay. Tom, I'm going to let you do maybe a little technology before I come back with a couple more. How about that?
Sure.
All right.
Do that.
All right. I'm going to stop sharing. I'll let you do a little technology. I'll come back and talk about some continuous functions. Okay.
Okay. Sounds good.
There you go.
So, all right. And I'm going to share my screen. And you guys can give me some feedback, see if you're seeing my TI-84.
Indeed.
I am seeing yours TI-84 plus CE.
Okay. All right. Great.
So hold on, Tom. I've got one question while you're setting this up. If you always, this came from Maureen Buys, says if you always approach or if you always default by using a limit with the outer function, would that be a good practice?
Well, I think the good practice is, Tom, correct me if I'm wrong, but I think the best practice is to see what is the inner function doing and then examine, well, what is the outer function doing as the inner function approaches that particular value? If you happen to know that the inner function is continuous and you can find that limit, well, then you can just plug that answer into the outer function.
Okay. Yeah, I agree with that. And I apologize, Maureen. I think I said your name wrong. It's probably Bees. So apologies there. Go ahead, Tom.
Sure. So, Steve, if I'm not mistaken, there was someone had posed a question about just better understanding why is the limit as x approaches 0 of the sine of x over x equal to 1.
Yep. It's my last one today. Yep. Great question.
One of these kind of very classic limits we hit. And it's one of those that really defies the factoring strategy that we do with rational functions so often, and where we look for that common factor and just not going to be able to deal with a transcendental function like sine x. So what I decided to do is I've put up a graph here. I don't know if you can identify that what I've graphed here. What do you think, Curtis?
As x approaches 0?
No, just what is this a graph?
Oh, what is this graph? What is this a graph of? Well, Tom, you haven't given me any kind of scale. I've played this game too many times.
The scaling is equal on both directions.
The scale is equal in both directions.
I don't have any kind of weird scaling going on here.
Okay.
The units being really different in x and y. Yeah. No.
You could still be doing something really funny on me in that this is a calculator window. And I could have a magnifying glass out on this particular function, but in this viewing window you've given me, it sure looks an awful lot like something along the lines of y equals x, because I know the calculator is not a rectangle or not a square window. So I'm going to say it's y equals x. Okay. I'm going to take the bait.
Okay. All right. Which is exactly the bait you should have taken. It really looks like y equals x for all intents and purposes. And so I'm just going to zoom out on this function.
It still looks like y equals x.
Sure does, doesn't it?
Oh man, you got me.
I'm starting to see a little bit of curvature to it. And I think now I'm back to just a regular window here. You know, I'm not claiming this as a proof. In fact, I mean, the proofs that you see in calculus books about why the limit of sine x over x, almost all of them involve quite a bit of geometry and arguments about, you know, comparing an arc length to a, and they're really difficult. But really, the punchline here is up close, near zero. Those two functions behave a lot alike. In fact, the closer you get to x equals 0, the less you can distinguish sine x from x. Okay, so that's, and I think in terms of understanding why that limit is equal to 1, you know, I find this a really compelling picture. I want a big qualifier there. It's not a proof, but I find it incredibly convincing for my intuition as, oh, okay, that's what's really going on here. So that's what I wanted to really start out with. I was curious. I don't want the problem you just looked at, Steve. Yes. I was kind of playing around with it and actually trying to come up with some formulas for that function f and g. And we thought we might try to illustrate that with a calculator.
Okay.
Actually try to look at that limit in another way.
Okay.
By the way, I really liked your analysis of it, and that was really nice. So I took some notes, and I think I came up with some formulas for it. But as you could tell, both of those functions they're going to require some piecewise definitions.
Mm-hmm.
So I'm going to go to a y equals menu here. And I've got actually one piecewise definition in here already, but that's for another problem. Let me go down to Y4 here and see if I can try to get these two piecewise definitions in. And folks that haven't, I find that's one thing on the 84. Sometimes people aren't aware that they can do a piecewise definition of a function very, very easily. So let's illustrate how you do that. So if you go to your math menu, and it doesn't stare at you right here, but if you go ahead and scroll down all the way to B, get past the numbers, it says piecewise. And that's what we want here. And let's see, I think the first one I looked at, it looked like two pieces. It looked like it was a part of a parabola. Mm-hmm. And then it was also a constant function.
Right.
So I think we just have two pieces. So I'm going to lower the number of pieces to 2. And that's okay. And then it gives me this nice little template for entering a piecewise defined function. Now I've done a little bit of the side work here. I had to, you know, look at that parabola and figure out what was the equation of that parabola. And if I'm not mistaken, I think it was actually 5 minus x squared. So I'm going to enter 5 minus x squared. And that formula was valid for the values of x that were less than 1, strictly less than 1.
It was less than 2, maybe, Tom?
Less than 2? Okay. You're right. Okay. So let me put in x, and then I'm going to pull up the inequality off the test menu. And there's number 5 is less than 2. So that was the first piece of the formula. And then the other was, I think it was just a constant -1, right?
Right.
Okay. So let's put in -1. Got to remember to use that negative sign and not the minus sign for subtraction. And then we'll have x again. This will be for greater than or equal to 1. So let me again go to the test menu. Oops, got on the wrong one there.
Hey, Tom, I'm late to the party here, so I won't be able to help you on this particular one. But for future, when you go to that test menu, note that up at the top, there's the conditions, and you can use those, which are really handy for like, especially when you're
the compound
complex things where you've got combinations there and you need that and in there.
Yeah, absolutely. So here with just these, with just 2 pieces, we had a pretty simple inequality. So we pulled it off the test menu. And so this was for x greater than or equal to 2. That formula is valid. So I think that's a valid formula. And just do a reality check on that. Let me go ahead and graph it and see if it looks like your picture did. So, okay, and that magenta graph looks like what we had before. Now let's see if we can tackle that other one. I'll put it down in Y5.
Tom, you're already showing people things they didn't know. So good.
Oh, well, I think, you know, Piecewise is one of those big ones, I think.
Yeah. This is a nice, powerful piece of the TI-84. Being able to introduce those here.
And Steve, I don't know if you had done this yourself, but you can check me on my formula. I think one of these pieces, well, you could do it in a lot of different pieces, I guess. Yeah. I'm going to go ahead and do it in just 2 pieces. So let me do the, let me pull up that math menu again. I'll actually scroll up to get to the end of it. There's my Piecewise. And I'm actually going to try to do it in just 2 pieces.
Okay.
And the way I'm going to do it in 2 pieces is actually make use of kind of a shifted absolute value thing. So that pointy cornered piece of the graph, you could do that as 2 linear pieces, but I'm going to give it a shot at trying 2 minus the absolute value of the quantity x plus 1. Because I think the corner point was right at -1.
Correct.
Okay. But the V shape we usually have for absolute value has been flipped over and shifted up 2. So here's how we're doing that. And the interval for which this was good. This is one where I'm going to make use of that condition suggestion that Curtis gave. This is really handy. So I'll go ahead and go to the test menu and scroll over to, go to conditions. And I think this was good for -3 less than x less than or equal to 1.
Correct.
Okay, so let's see. The first one's a less than, and the next one is a less than or equal. I think that's number 8. And actually, I should have put in the first number first, but I can just scroll over there and or cursor over there, and let's see. It was -3. It's less than x, and then x is also less than or equal to 1. And there's our definition. And what I like about this is this looks exactly like it would if you wrote out these piecewise definitions in a textbook. You've got your 2 formulas and the domains for each one. And the second part of the, go ahead, Curtis.
I'm just want to make sure that I make a comment here because we've got several people making comments in the chat here about excitement about using Piecewise and things of that nature. And then some questions around whether they have it or don't. So this is sort of a heads up. So Tom, you're using the TI-84 plus CE emulator, which is the current version of SmartView, and it's also the current calculators that we sell. But the older TI-84 plus and the older TI-83, neither of those will have the Piecewise template in the in the menus there, but you can still do piecewise functions on those. It just takes a bit more of the logic piece. You have to multiply or divide by some certain conditions in order to make those pieces happen. And so it's a little more challenging to do it on the older calculators. But if you've got an 84 plus CE, you can update to the latest operating system and you'll have that piecewise template in there. So I just want to make sure that we are clear about that you're using the TI-84 plus CE, the color editions, and the older grayscale ones. You can do piecewise, but it takes a little bit more logic, multipliers and things to make it happen.
That's right. Yeah, it's always been possible to do these. It's just the template is super nice in terms of it matching what we're used to seeing in textbook. So for the second piece of this was another, I think, absolute value piece. And if I figured it out right, I think it was 3 times the quantity x minus 2, and then the absolute value of that. I can see Steve is doing some calculations. Maybe he's checking me out here to see if that looks like that's going to work. I'm going to go, it's going to be for 1 less than x less than or equal to 3. So I'm going to go ahead and put in the 1 and then do that conditions again. This one, I think that's going to be number 8 again. Okay.
Yep. Mm-hmm.
Yeah. And then all we got to do is put in a 3. And I think, let's see if we can graph this one too.
Well, that's pretty cool.
Excellent. Okay. And the question on this one was actually about, now you have the 2 graphs side by side. Here they're superimposed on each other, so it's kind of interesting. You were looking at the composition,
right?
2 functions, right? So right. I wonder if we can do that. Could we actually graph the composition of these 2? Well, somebody just dared me to do it, I think.
Yes, I dare you to do that.
All right, I'll go ahead using it in Y2 here. So let's see, the Y4 was the F and the Y5 was the G.
Right.
And your order was G of F, right? I think.
G of F. So it's your Y.
Y5 of Y4.
4, right.
Okay.
Mm-hmm.
So let me go to my Y variables function. And we'll do Y5 of Y4.
This, Tom, is one of my favorite things about using the TI-84 plus CE for this, because you can do compositions of functions just exactly how you might write them out somewhere else.
Yes.
And I just love that it's visually exactly how you would do it. And this is something you can do on all the TI-84 and 83 family calculators. It's always been a thing to be able to do input 2 functions and then do compositions of them, both on the home screen, on the graph screen as well.
Yeah. And it's kind of a test-taking tip too.
For sure.
On that calculator active part of the exam is actually defining your function kind of once and for all if it's given to you in the problem, and then referring to that name, both in terms of what you write down and in terms of calculations. For example, if I was trying to take a derivative of a complicated function, re-entering that as I'm trying to calculate the derivative, it's just that much more opportunity for making typo or mistake.
Yep.
Yeah.
So, Tom, while you're saying that, just so that I'm clear, on my response, I can name my function f of whatever is this, and then I can just use f later on, or in this case, I could define it as y5 is this and let it, and then I could reuse that later.
Yeah. So, for example, if a function is defined on the exam given to you, you can refer to it by its name, but you can also declare a name for a new, not one that's already been used in the problem, but you say, hey, I'm going to call the function G this, and then just refer to G later on. And
Right.
the folks that are grading the exam will take what you said quite literally and say, oh, they've defined what they mean by G, so it's unambiguous.
Yeah.
So
I think that's a really great tip. Another tip was given just a moment ago about how to find your Y variables on the calculator. Instead of going through the vars key, if you use the alpha F4, which is the trace key, all of those Y variables are underneath of that as well.
So you're saying do an alpha trace.
And that should pop up. That should pop up all of your
Very nice.
all of
very
your Y
nice.
variables. Yes.
Very cool. Okay. All right, I'm going to go ahead and graph. And we're seeing now a graph of the composition of these two functions.
Oh no, that's a great composition.
And I'm wondering let's see, is some of this maybe off the screen? No.
Looks like it's up high here.
Yeah, so I might do a quick zoom, maybe a zoom out just to see a little bit more.
So while we're zooming out, it looks we put a poll on the chat just to find out what variety of calculator everyone is using. So just of some interest as we continue going on through these, we want to make sure we're showing what people are using. Looks like most have the 84.
Okay.
So Tom, this is
Yeah.
an interesting question. There does not appear to be any part of that composition. Oh, I'm going to just quickly say between -1 and +1, something like that. There seems to be a part of it missing. So I'm going to go out on a limb here and say, I don't think you're missing it on your graph. I think there may be some other reasons why it's missing.
Oh,
Okay. So maybe we can reason through.
Maybe we should leave that for the chat.
I think we should. I think there's some interesting things because which way are we going? Are we going from which is our interior function? Magenta?
The interior one is F.
Well, I know that. I don't remember which one we defined as the magenta one.
So the
magenta-
F function is the magenta one.
Right.
Okay, thank you.
Green one function is our G.
Okay.
And the red one is the composition of G composed with F.
All right. Well, now I'm with Steve. I think that's a good idea.
That's good. Yeah.
And we were interested in what was going on with that composition as you approached
Two from the
both
left.
the left and the right.
Mhm.
Okay. So I'm going to go ahead and turn on the trace. And this is some verification of what Steve posited, was that there is no graph for some interval in the middle here, because at x equals 0, we have no y value for that composition.
And the
Now I
question
want to
is
trace
why?
over toward 2.
Okay.
Now I'm just, because I started at 0, I'm going to be coming in from the left.
Okay.
So at x equal 1.5, that's the first, at least trace value that I started picking up something.
Yep.
Okay, now we would need to analyze it more carefully, but it looks like now we're finally to where we can approach x equal 2 from the left-hand side.
Mm-hmm.
The y values look like they're approaching We might not
2?
have. Did I make a mistake? Maybe. Was it approaching 2? Is that what we came up with before?
We came up with 3.
We came up with 3 as we came from
From the
Right.
left-hand side.
from the left. Yeah.
Okay, now I don't want to put in exactly 2, right? Because if I put in exactly 2, what would I get?
2.
2. And so that is correct. That is the actual value as at 2.
That's
Yep.
correct.
That's
That is
correct.
correct.
That is the actual value. I think what's happening here is a lot's going on between 1.9
Mhm.
and 2.
Yep.
So I think we want to maybe use our window here and get another look at this, except let's do an X interval here where we go much more close to 2. I'm going to go from negative, excuse me, let me delete that. How about we go from 1.5 just to 2.5? So that's going to be using the whole screen for just an interval of length 1.
Oh, a good suggestion there about a table too.
Ah, okay. Now here's our 3 graphs. Remember, the red one is the composition.
Well, that looks a little better, doesn't it?
It does. Oh, look at this. So as we
Yeah.
approach 2 from the left-hand side, it's approaching 3.
Yep.
And if you approach 2 from the right-hand side, so as you said, it's actually a constant 2 coming in.
So
And
Tom,
again,
this is I think this is a great demonstration of the importance of being able to zoom in and zoom out and really do that visual investigation. And I think something similar could be done on the table. If you went in and adjusted your table and did some fun things there. But I want to make sure we give Steve a chance also to.
Yeah, and exactly. So yes, looking at a table of values, or just going to the calculator screen and substituting in a value that's close to 2 from the left and the right. It's a really powerful way to do it. Just evaluate.
Really nice, just evaluation as a way to check that. Yeah.
Okay. All right.
All right.
Steve, I'm going to go ahead and turn it back over to you.
Okay,
So
yeah.
I'll do a stop share so that you can.
So
right.
Maureen, as you guys are switching, Maureen gives us the suggestion that, yeah, she goes into the table and does
Very
the table setup and changes it, the independent variable to ask. And then and Michael Carson says the same thing, put the independent variable in the ask mode, and then you can type those values in and watch it approach. So both doing that on the home screen or in the table view are both powerful ways to do that. In fact, I would encourage maybe even do the split table, graph table view as well, right? So you can have that visual on the left-hand side and then put those values in on the right.
Well, this is a good problem. I wish we could say that, Curtis, that we planned it this way, but here's a nice piecewise function now that people could practice on with their TI-84.
We planned it this way. We know we did.
This is a great question, too. It says, determine the values for x for which this function is continuous. And there's a lot of cool things going on here. Now, let me see if I can get through this one because I got a couple of others that I'd really like to look at. So I'm going to scribble off to the side here. Not everyone does this the same way, but when I think about a function be continuous at a specific value, let's say x equal to a, I want to check 3 things. So the first thing I want to know is f of a defined? I want to know if the limit as x approaches a of f of x, I want to know if that exists. And then finally, I want to know if these 2 values are the same. So I want to know if the limit as x goes to a of f of x is equal to f of a. If those 3 things are true, then indeed the function is continuous at that value a. Now, some people just talk about continuity in terms of this last step, and that's fine too. The limit as x goes to a of f of x equal to f of a. That 3rd step does in fact encompass the first 2. But for my money, I like parsing this out and looking at these 3 things separately. So let's take a quick peek at this one. Find all the values for which this function is continuous. Well, all right, I'm going to take a look at this, of course, in pieces. So let's look at this first piece for x less than 1. Well, I know that 1 over x is defined everywhere except that x equals 0. And I know a lot about this function. I know what that looks like in general. I know that f is discontinuous at x equals 0. I know I can't plug in an x equals 0 there. I know it's discontinuous there. So the other places that I have to check, just looking at this, are sort of these cutoff values. I've got to look at x equal 1, 2, and x equal 8. And there's some cool stuff going on here. So here's x equal 1. First thing I'm going to try to do is to figure, well, is f defined at 1? Well, let's see, f of 1. Whoops, I'm sorry, I went up too far there. What's f of 1? Well, according to this inequality, I've got to plug it in here. So that's 1 squared, which is 1. So let's see, is f defined at 1? Yes. Now, how do I find the limit as x goes to 1? Well, unfortunately, maybe I've got to take a look at two one-sided limits. So as x goes to 1 from the left-hand side, let's see, I'm approaching 1 from the left-hand side, so the function f looks like this from the left, 1 over x. How do I evaluate that limit? By direct substitution, so that value is 1. Not done. As x approaches 1 from the right-hand side, the function looks like, I apologize, looks like this, x squared. That's a simple polynomial. I can plug in 1 there, and in fact, the limit from the right-hand side is 1. So, all right, I put all this together. The overall limit is 1. That's equal to the value of f at 1. So I know the function is continuous at 1. I've got to check at x equal 2. Well, this is a little sneaky. I wouldn't do this to anyone in my class. But you'll notice.
Sure you would, Steve.
No, I wouldn't. I wouldn't. This function f is not defined at x equal 2. So it's not defined there. So darn it, it can't be continuous there.
Boy, that is a really sneaky,
Isn't that sneaky? Yeah.
definition there.
And
sure.
This is clever too. I like this one. What about at x equal to 8? Well, f of 8 is equal to, well, let's see. That would mean I would plug it into this expression. That would be the square root of 8 times 8. There's some little things going on here too. What's the square root of 64? Some of our students would say, well, it's plus or minus 8. No, it isn't. The square root is a function and it only returns the positive square root. So the square root of 64 is 8. Now I've got to take a look at the limit as x approaches 8 from the left and from the right. Well, from the left, it's this. It's going to be 8. And son of a gun, coming at f from the 8 from the right-hand side, it's 8.0001. And as much as we'd like to call that 8, it isn't. And so that overall limit does not exist. So
that would be a great one to throw up on the calculator too, and just
see
do the whole conversation about, okay, just because it looks this way.
That's right.
You know what they say, Steve?
What's that?
Close only counts in horseshoes and hand grenades.
And not in functions. Thank you very much. So, to finish this one up.
Oh, wow, Tom.
Here we go, back here.
Oh, wow.
F is continuous everywhere, but at 0, 2, and 8. Nice problem. I think a good one for practicing technology also. And I'd like to take a look at this one too. This was an excellent problem too that was posted on the Facebook page. This time we don't have graphs given to us, but we're given two piecewise functions, u and r, very interesting functions. And we're asked to find the limit as x goes to 0 of u of x divided by r of x. Now, our initial inclination here, I'm just going to scribble a little bit. Our initial inclination is to try to do something like this. The limit as x goes to 0 of u of x divided by the limit as x goes to 0, that's a limit right there, as x goes to 0 of r of x. Curtis, just a little bit of housekeeping here. We're experiencing some severe thunderstorms in our area, so if you lose me, you'll know why, okay?
Okay. Okay.
All right.
Well, hopefully you're all right. Stay safe.
I'd like to do this, but I can't. I can only split this up, this limit of a quotient, into the quotient of limits if both of these limits exist. And if you take a quick look at this function u here, as I come in at 0 from the left, it's approaching 2, and 0 from the right, it's approaching -2. So that limit in the numerator does not exist. I cannot split this original limit up like this. I'd like to, but I can't. So what does that mean? I've got to sort of break this down, kind of like I did with the composition function, and try to argue here, what's this quotient doing? Okay. So I'm going to take a look at the limit as x goes to 0 from the left and from the right, given the nature of the definition of these two functions. As x goes to 0 from the left, let's see here, I'm going to write this in kind of a weird way. As x goes to 0 from the left-hand side, what's u doing? Well, let's see. As I approach 0 from the left-hand side.
Wow.
Can you hear that?
Oh boy, we can hear it, Steve. You are working under stressful conditions.
U of x is going to 2. It's constant. So the numerator looks like 2. What's the denominator doing? Well, as x goes to 0 from the left-hand side. So you got to take a look at this expression. X is getting close to 0 from the left. X is getting close to 0 from the left. And the way that I like to write that in my class is just a negative sign in parentheses. That's an indication that that denominator is getting very, very small negative. So the numerator is 2. The denominator is approaching very small negative numbers, and that drives the whole expression, the whole fraction, to minus infinity, decreasing without bound.
Agree.
Now, similarly, as x approaches 0 from the right-hand side, let's see, this time the numerator is going to minus 2. And this time, let's see, the denominator is approaching 0, but this time through small positive.
So Steve, this is a very creative, oh, I think we may have lost him on that last lightning bolt there. I'm just gonna guess that that's probably what has happened, that we've lost Steve on the last lightning bolt there. Hopefully he is all right. But I agree with Gerald. I just saw your comment there that this is a very creative problem. And Tom, I think we can kind of see what was about to happen here, that this was quickly going to approach negative infinity also from the right-hand side, right? And since, and Tom, I'll let you take it from there. If maybe you want to share your screen for a minute and then we'll wrap up. Do you want to show a quick graph of that? Or do you want to just
actually, I think Steve had a graph of it at the bottom, and it
looked pretty much.
Yeah.
Okay. Well, that's fine.
And it verified, so that's good. Yeah.
So what I'm going to do then is I'm going to call an audible here. Tom, do you have anything else that you wanted to share on this, or?
No, I think the one comment, the problem that Steve was looking at before this one, which was another one of those split define ones that are leaving to people to try on their own, that place where it's close, where it's approaching 8 from one side and it's constant 8.0001.
Yeah.
That's one where I think the graphing technology is really good again, because you can zoom in at that point. And, at regular scaling, it looks like, for all intents and purposes, like it's continuous. But when you zoom in, you sure enough see the break.
Yep.
I think that's a good use of the zooming capabilities of your calculator.
Yeah, for sure. For sure. Well, I'll do this then. I will just thank you and Steve for your time this evening, and I'll also thank everyone else for logging in. I do want to make a couple of plugs right before we go. First of all, we've got a blog on the TI website that lines out the schedule of the dates and times for each of these sessions that we're going to be doing this fall. We're going to actually be doing 7 of them, including this evening, and we highly encourage. I noticed that there were a couple of students who were involved this evening, and I want to just continue to encourage teachers to go ahead and invite your students to log into this and ask questions and pose answers on the chat. What a great way. I saw several people answering questions and asking questions through the chat all this evening. And what a better way to have students see that even us as adults are asking questions and not afraid to ask them, and then providing answers and getting those answers there. So use this as a great resource. Steve and Tom, very knowledgeable guys. We really appreciate them volunteering to do this with us here. And so hopefully you've enjoyed this evening. I've certainly enjoyed it. I had a good time, and look forward to seeing you guys in the next session. It's going to be 2 weeks from this evening, which would make that September 27th, I believe, at 7 p.m. Eastern time. We'll be starting again. And then I'll make sure that blog is posted in the chat. Looks like Steve is actually going to get back on for us. So Steve, I just want to thank you for this evening. We talked briefly about the graph that you had there and how things were going to trend off to negative infinity. It was pretty good picture of what we assumed to be happening. So great on that. And I'm also just thankful, grateful for you giving your time to be able to do this. So thanks very much.
A lot of fun.
And with that, I think we'll wrap it up, and we'll see you guys in a couple of weeks.
Great.
Great. Bye,
Thank you,
everybody.
Curtis.
Bye, everyone.